Good day, I'm Dr. T and welcome to my office. So today I would like to talk a little bit about nuclear power because no discussion of radioactive isotopes would be complete without a discussion of nuclear power. Okay, so the fundamental physics that allows nuclear power to be a thing is known as the mass defect. In short, protons and neutrons, their mass isn't the same. Their mass is dependent on what nucleus they happen to be in, or if they are in a nucleus. By changing the element, you are able to change the mass of the protons and neutrons in that, and that mass doesn't just go away in a mass particle. It goes away and is converted into energy by the equation E equals mc squared. E is energy, m is mass, and c squared is the speed of light squared. Yeah, that's a big number, so that means a small change in mass will be a huge amount of energy. Admittedly, we are talking individual atoms, so one atom doesn't change that much mass, so it's still a very small amount of energy for one atom. However, if you rig things right, you can have it a lot more than one atom. There's two ways to release a fairly large amount of energy in a reasonably short period of time. The one that takes place naturally in our sun, as well as all other stars, is fusion. In this case, you take, under incredibly extreme conditions, high temperature and pressure, atoms that are fairly small. They need to be less than the mass of iron, and smush them together to form a heavier atom. The reason they need to be less than the mass of iron is because once you exceed the mass of iron, the protons and neutrons start going up in mass. Now, when it comes to fusion, this in a nice controlled power source would be a wonderful thing. And we've been trying to do so for the last 50 years or more. However, we have not succeeded. The conditions are so extreme that we cannot do so in a controlled fashion at this time, at least not on Earth. Obviously, the sun. So a solar cell is a fusion reactor, sort of. It's not really the reactor, but it's accepting energy from the sun, which is a fusion reacting ball of plasma. Now, if you want to go for an uncontrolled release of the energy, that would be what you would see in a hydrogen bomb. In this case, an atomic bomb, which I will discuss in the next section of this video, is used to create the extreme conditions and squish either hydrogen or, more typically, lithium, because it's easier to work with. And with that intense energy, you're able to start a fusion reaction. Now, let's talk about those atomic bombs and nuclear power plants, because those both rely on fission. So in this case, we're going to take a large element, something like uranium, and it needs to have an isotope that's going to be able to relatively easily split. Certain large elements are capable of doing this, others not so much, and different isotopes do matter. So uranium-238 doesn't split very well. Uranium-235, on the other hand, does split very nicely. So if you can take a nucleus of uranium-235, bombard it with a neutron going at just the right speed, then it will spontaneously split apart into two daughter nucleuses. The daughter nucleuses have less mass than the original uranium-235, and thus energy is released. Now, additionally to these two daughter nucleuses, there are three other neutrons, and those three other neutrons can hit other U-235 nucleuses, and thus contain a chain reaction. Now, for civilian purposes, if you wish to make a nice controlled release of energy, what you want to have is a single neutron from each nuclear split hit another U-235, and for that to split. To do this, you obviously want to make sure you have the uranium-235 packed in close enough, what we refer to as enriched uranium, because naturally occurring uranium doesn't have enough U-235 to sustain a nuclear reaction. But you don't want so many neutrons flying around that multiple neutrons engage with other uranium atoms, thus causing the thing to go supercritical, increasing the amount of energy coming out of itself exponentially. Therefore, control rods, which are used to suck up neutrons and prevent them from colliding with other uranium-235 nucleuses, are used, and thus to create a delicate balance in the controlled nuclear reaction, which is used to generate heat. The heat is then used to heat water, and the water is used to turn a steam turbine. Now, if instead of a nice controlled civilian application, you just want to blow something up, then you want to have as many neutrons as possible hit uranium-235 atoms, and cause them to split. Alternatively, plutonium is another choice instead of uranium-235, because in this case you need a highly enriched uranium with lots and lots of uranium-235 in order to cause a very massive cascade and thus release the energy very, very quickly. But, as has been seen with the detonation of nuclear bombs, you can definitely release a lot of energy very, very quickly when doing this. Now, when it comes to the practical applications of this technology, whether it be blowing stuff up or creating nuclear power, obviously with everything there are advantages and disadvantages to which I am not going to get into. So with that said, have a wonderful day.